Okay. Alright, so let's go ahead and get started. I should have the exams graded and passed back by tomorrow. We'll see how everybody does. I might have to curve it by a couple points again, so we'll see. So again, I'll have exams back by tomorrow. We just have 2 chapters left for the rest of the quarter. Chapter 6, which is about essentially trigonometric identities and verifying identities using a bunch of properties. There's a little bit of solving trigonometric equations as well in each section. So we're going to take equations that we solved earlier, and then basically now we're going to solve some more difficult equations, but we'll be using identities to first simplify the equation so that we can solve it. Chapter 7 we'll study what are called parametric equations and polar curves. Those will show up later on in a calculus class. And let's see, what else? Other announcements. This Wednesday we will not have class on advising day. So make sure if you have time, go see your advisors. This Friday we will not have class because I will be gone at a math conference. I think what I'll do is I will post a video on Thursday so that everybody can watch and that you'll have some familiarity with what I talk about on Monday in class. So again, no class Wednesday, no formal class Friday, but I will post some short 30-minute video just to have everybody watch over the weekend. And exams will be passed back tomorrow. Okay. Other announcement. Homework for this is also posted. There's an online component and a written component, and that's scheduled to be due Thursday. Okay, so we'll have 2 days covering 6.1. Wednesday is advising day. I can still meet maybe in my, let's see, if nobody schedules an appointment for advising, I'll still be up in the TLC from 1:30 to 2:30 on Wednesday. You could still possibly schedule an appointment with me or send me emails and I should be able to get back to you. Okay, so this section, this whole chapter is all about what are called fundamental identities, trig identities. This section is just about what we call the fundamental identities. So the two main tasks in this section, one is going to be using our fundamental identities to verify that identities are true, and then the other portion is to use identities to solve equations. So before we do that, I have to tell everybody what the difference between an equation and an identity is. So I'll just write the definition. So difference between So what is the difference between an equation and an identity? Okay. So the first definition, an expression an expression that is true for all values of the variable is called an identity. And we've seen some of these already. Expressing, an expression. Must have been a long weekend for me. So an expression that's true for all values of the given variable is called an identity. An expression that is true for some values of the variable is called an equation. And then of course an equation, right, you might only have 1 or 2 or 3 answers, whereas in an identity it doesn't matter what you plug in, the expression will be true. So I'll do an example of each. So I'll remind you, I'll write down an identity and an equation, a trigonometric one. And then I'll write down one you might have seen in a pre-calculus course, or pre-cal 1. So anybody know of any identities we know of so far? Okay, so there's the Pythagorean identities. So for instance, sine squared theta plus cosine squared theta equals 1 is true for all values of theta. Okay, so that's why that would be an identity, right? It's true for all values of the given variable. So there's nothing to really solve for there. Right? You can plug in any angle that you want and that expression would always be true. Or I can think of an equation like 2 sine squared theta plus 1 equals 0. Okay, this is true for only some angles theta. Right? You can't just plug anything you want into the second expression and get a true equality, but you can plug anything you want into the Pythagorean identity. Okay, that would be a true expression for all angles, whereas this is only true for some angles. Okay. And we'll get to solving these by the end of class. Here's another example of an identity. Okay, so maybe you've seen in a previous class the square root of x squared is the absolute value of x. That is true for all values of x. But if I get rid of the absolute value on the right, this is true only when x is greater than 0, whereas this is true for all values of x. If you plug a negative number on the left, like -1, -1 squared is positive, and when you take a square root, it's positive. But you won't get the right-hand side would not be the same when x is -1. And we're going to do another couple examples here in a second. So that's why an identity you can't really solve for because it's true for everything. We only solve equations because they're only true for some specific values of the variable. And what we're going to be doing, we'll be doing a couple things. We'll be either verifying identities are true, or we'll be solving an equation, okay, when the expression is not true for all values of the variable. All right, any questions so far? Everybody get the basic gist? This will be the first test as well, where I will be letting you use some equations and identities on the test, so you won't have to memorize everything this time. You'll have to memorize some of the core identities, and then there's a bunch of other identities that I will provide to you for free. Okay, so this will be the first exam where you don't have to memorize every little piece of information. Yay! Okay.
Will we know what does and does not need to be memorized?
Yes, I will give you a sheet that has all the... I'll give you a sheet, basically. The stuff you have to memorize will be blank, and the stuff that you get to use will be on that sheet. And I will provide it before the exam as well. That way you'll have time to practice the things you need to have memorized. Okay. Does that answer your question? Okay. All right, so example 1. And this isn't really a trigonometry type of question, but it's going to get us somewhat used to what we'll be doing here in just a minute. So verify the identity x minus 2 squared equals x squared minus 4x plus 4. Okay. Now remember, since this is an identity, there's nothing to solve for here. Essentially what we need to do is just use algebra and show that the left-hand side is the same as the right-hand side. Okay, so what we're going to do is we start with the left-hand side of the expression and try to simplify until we get the right-hand side. And let me stick to my is it acronym? Yeah. So everybody okay if I use LHS and RHS for left-hand side and right-hand side? Okay. And the same will be true when we start showing that trig identities are true. You'll pick one side of the equation or the other, okay, just one of them, and you will try to simplify that side until it looks identical to the other side. Okay, so start with, as I said, the left-hand side. Okay, so x minus 2 squared. And remember, when you square something, that's the same as multiplying by itself. And then you would have to do what here? Okay, you'd have to FOIL, if you like that terminology. Okay, so you'll have to distribute the x to both terms on the right and the minus 2 to both terms on the right. X times x is x squared. X times negative 2 is a minus 2x. So that's what you get when you do the first distribution. And then I'll take negative 2 and multiply it by both terms. Negative 2 times x is minus 2x. And then I'll get a minus 2 times a minus 2, which will give me a plus 4. And that'll simplify to x squared minus 4x plus 4. And was that what the right-hand side was supposed to be? Okay. So what you can do is you can put a little check mark, right? I verified when I took one side of the expression and I simplified down to the right-hand side, we got the same thing. Okay. And of course, since the left-hand side really, after simplifying, equals the right-hand side, this is an identity. It doesn't matter what x you plug in, both sides of the equation would be the same value. Okay. So here's anybody have any questions on that one? If I wanted to verify that this expression was true for all values of x, you just show that one side equals the other side and you move on. So you'd be done. Okay, and then example 2, question, is the expression x squared minus 4x plus 4 equals 2x minus 4 an equation or an identity? Sorry, and I should have put a question mark there, since that is technically a question. So what do you think? Is that expression true for all values of x, or just for some, perhaps? Some. Okay, so some of you say it's just true for certain values, right? In fact, if you look at the previous example, the x squared minus 4x plus 4, the only thing you could do is factor it, and it's identically equal to x minus 2 squared. Okay. So this is an equation since it's only true for certain values of x. Okay. And in this case, I think the only thing that's going to end up working is positive 2. You could verify that on your own. But for example, if I plug in 0, I think it's clear you don't get the same thing. Right? So the left-hand side at x equals 0 is 4. Okay, and then what do you get on the right-hand side when you plug in 0? You plug in 0 on the right-hand side, 2 times 0 minus 4 is negative 4. That's just an example of why it would not be an identity. Right? I found an x value for which both sides are not the same.
So we have to show that?
Yeah, if I asked if something was an equation or an identity, generally what you'll do is you'll pick a specific value in which both sides have a different outcome or value. Okay. So yeah, if I want to show that it's not an identity but it's really an equation, you can just pick one value of x and say the left-hand side is 4, but the right-hand side would be negative 4. So it's not an identity, it is an equation. You could go on and solve for it if you liked as well. I mean, if you wanted to solve for it, you'd have to subtract the 2x and add the 4. So if we solve it, you'd get x squared minus 6x plus 8 equals 0, which factors as x minus 2, x minus 4 equals 0. Right? And the only values that make that expression true would be 2 or 4. Okay. Now, generally, we're not going to worry about stuff like this. Again, I'm just trying to get the idea across of what's an equation and what's an identity using something familiar, right? Our polynomial expressions from pre-cal 1. Okay. So, questions on the test. You might have a couple on the homework asking you if they're equations or identities when they're just polynomials. But on the test, there won't be any pre-cal 1 stuff. Okay, it'll all involve trig functions. Okay. So again, I was just trying to get everybody used to what's an equation, what's an identity. If it's true for all values of the variable, it's an identity. If it's only true for some values of the variable, it's an equation. Okay, so same idea. So if I want to show something is not an identity, I have to pick a particular value of the variable where both sides give me a different value. So we might have seen this earlier, but show that arc cosine of cosine of x, if I can write, equals x is not an identity. Now, as a matter of fact, yeah, when you do the inverse trig function on the outside and the regular function on the inside, they don't just cancel each other out and always give you back x. It only works for certain values. Okay, so if I want to show this isn't an identity, I have to pick an x value and show the left-hand side and right-hand side are different for that x value. So anybody have an idea? If you try 0, I don't think 0 will work because cosine of 0 is 1, and then arc cosine of 1 would be 0, and I'd still get 0 on the right. In fact, it has to be something that's outside of 0 and pi. So for example...
3.2.
Huh?
3.2.
3.2 would probably work.
Why don't you just use 10?
Use what?
10.
10 would be one that we could use as well.
I tried it.
You did 3.2?
It has many zeros and then a 1.
Okay. So it doesn't really matter. So just like you said 3.2, I'll go with Claire's 10. Because Reed, you already exemplified that when you plug 3.2 in the left, you don't get back 3.2. So if the right-hand side is going to be, say we use 10. Okay, so the right-hand side is going to be 10. Or let me say this. The right-hand side, when x equals 10, is 10. But the left-hand side, when x equals 10, what do you get when you plug that into your calculator if you do arc cosine of cosine of 10?
You got 10.
How does that work, though? Because arc cosine is supposed to only spit out numbers between 0 and pi. Let me try. Are you guys in degree mode or radian mode?
They're in degrees.
Yeah, go back into radian mode. Because if you're in degrees, you're between 0 and pi if you choose 10. So switch your calculator into radian mode. We're going to be back in radians for this section too, by the way. Okay, or for this chapter. So now we can put our calculators back in radian mode. If I do cosine inverse of cosine of 10, the left-hand side is actually 2.7, approximately. Okay. So when x is 10, the right-hand side would be 10. But the left-hand side, if x is 10 radians, is going to be about 2.57. Okay. So we have found a particular x value so that when you plug it in the left-hand side and in the right-hand side, you get different values. Okay, so this implies arc cosine of x equals x is not an identity. Okay. I was going to use something like 5 pi over 4. Okay,
3
but
pi over 2.
Yeah, or 3 pi over 2.
Anything, but third and fourth quadrants and then unit circles.
Yeah, because I think when you plug 3 pi over 2 in, you get like pi over 2 on the left.
Yeah.
And you get 3 pi over 2 on the right. Okay, so anything outside of 0 and pi, this will not be you won't get the same value on both sides. Okay, so that means it's not an identity. It's not true for all values of x. Technically, this is an equation. Okay. All right, so that's the whole point. For something to be an identity, it has to be true for all values of the variable. Okay, if there's at least one value of the variable where both sides are not equal, it's an equation. Okay, so now what we're going to do is we're going to look at identities exclusively. I'm going to give you some new identities that we haven't had up to this point. So flip over to the next page. And the new identities are what are called complementary angle identities. Right? We've seen the Pythagorean identities. We've seen the quotient identities for cosecant, secant, cotangent. We've seen the even and odd identities. I did write down the supplementary angle identities at some point. We didn't use them very often. And then, like I said, these are the new identities. So what I'm going to do first is I'm going to derive them for everybody, show you where these come from. Okay, so take a right triangle with the angle in the bottom left called theta. And if that's theta, what's going to be the angle up here in the upper right corner? So all three, well, I guess this angle plus this angle have to add up to 90 degrees because you've already got a 90-degree angle. Yep, so it'd have to be 90 minus theta, or in radians, pi over 2 minus theta. Okay. And then let's see. I don't know what you want to call these sides, but I'm just going to label them A, B, and C. And I'm going to do sine and cosine tangent of each of these angles. So say I want to do sine theta, that's B over C. Cosine theta is going to be A over B. And tangent theta is going to be B over A. And then watch what happens now when I do, say I want to look at this other angle now, cosine pi over 2 minus theta. So this time the adjacent side is B and the hypotenuse is C. So this is B over C. If I do sine of that pi over 2 minus theta angle, sine of this angle is op over hypotenuse. I also get A over C. And tangent, actually let me do it this way. For this one, you want to look at cotangent pi over 2 minus theta. Cotangent pi over 2 minus theta is adjacent over opposite. So you'd also get B over A.
Shouldn't the cosine be over C?
For which one? Oh, yeah, this should be A over C. Thank you. Is that the one you meant?
Yes.
Yep. And then all these identities are just now equated. So we know sine theta is the same as cosine pi over 2 minus theta. We know that cosine theta is A over C, but sine of pi over 2 minus theta is also A over C. So So that's why I at least did 3 of these. There's still 3 more of them, but now I know sine pi over 2 minus theta is cosine theta. We know that cosine pi over 2 minus theta is the same as sine theta. And I know that tangent pi over 2 minus theta is the same as cotangent theta, and vice versa. Actually, I did it this way, didn't I? So those are the 3 that I just showed, and then I don't think it's too hard to believe the other ones on the paper. Okay. So I could do the same for secant and cosecant as well. All right. So with that, and all your previous identities, the box at the bottom of the page, those are what we're going to call the fundamental identities. Okay. So you've got the quotient identities, Pythagorean, even, odd, supplementary, and complementary. And like I said, all of those can be proven by just looking at a right triangle. What else did I want to mention at this point? One other thing I wanted to mention. Some of these now make sense in terms of transformations. Okay. Really, this is saying that cosine of theta is the graph of sine with a phase shift of pi over 2 units to the left, and the negative sign is a horizontal reflection. Okay, so you can think of these in terms of reflections and transformations of the graphs as well. Okay, I think the easy way to obtain these, though, is just looking at the right triangle. Okay, how are we doing on time? Almost 10? Okay, we're doing all right. Okay, so example 4. I want to verify an expression using only the framed fundamental identities. Okay, so all the ones that are framed on the front page, those are what are called the fundamental identities. All the unframed identities can be derived from the framed ones. Okay, so if I know the framed ones, I can get all the rest of them on the bottom of the page. Now there is a typo on example 4, so make sure you fix this. It should say verify that tangent of pi over 2 minus theta. That should really say cotangent theta. So I shouldn't have minus tangent theta there. Okay, so make sure you fix the right-hand side. It should be cotangent theta. And we're going to use only the framed identities. This whole verifying identities part really becomes the most useful at the end of Calc 1 and somewhere in Calculus 2. Okay, so that's really where sometimes you're doing an application in Calc 1 or Calc 2 where an expression involving trig functions in the form given is not very easy or helpful to work with. So you simplify the expression using identities, and then it becomes easier to take a derivative or an integral or whatever the application is in calculus. All right, so I can only use the framed identities. Okay, so I'm going to come back to the previous page. And what we're going to do is we're going to start with the left-hand side and simplify into the right-hand side. Okay, so I'll start with what's on the left, and we'll do a bunch of simplifying using identities and hopefully be able to simplify it to cotangent theta. If we can, that's how we have then verified the identity. Remember, for an identity, there is nothing to solve. If you try to solve it, you'll get like 1 equals 1 or something like that, or 0 equals 0. Okay, so there's nothing to solve. It's just verifying using identities and simplifying. Okay, so let's start with the left-hand side. So tangent pi over 2 minus theta. Okay. And I want to see, we can only use the framed identities. So anybody have an idea of what I can maybe use first? So there's no squareds anywhere, so we can't use the Pythagorean identity. There's no minus sign. I don't think we can really use even odd.
Could use the identity of tangent.
Okay, so yeah, let's see what happens. I'll just go with that suggestion. Yep, we'll use the quotient identity for tangent. So tangent of an angle is always sine of that angle over cosine of that angle. Okay, so that's a good first step. Actually, let me do the equals over here. Okay. Anybody see now any identities that involve sine pi over 2 minus theta or cosine pi over 2 minus theta?
Yep.
Okay. So I think now we can use those two framed complementary angle identities. Okay. So what's sine of pi over 2 minus theta?
Cosine theta.
Okay, using the framed identity, that's cosine theta. Maybe I should have written some of these up because it's kind of hard to go back and forth. But and then what about cosine pi over 2 minus theta?
Sine theta.
Okay, if you look on the previous page at the bottom of the box, cosine pi over 2 minus theta is sine theta. Okay. And then, what can I do now?
Isn't that cotangent right there?
That is just our cotangent theta. So this is just the reciprocal of tangent, right? Tangent sine over cosine. That's just the reciprocal. That equals cotangent theta. And since we started with the left-hand side, we simplified using identities until we got the expression on the right-hand side. We're now done. We have verified that identity. Okay. Everybody okay there? So the first thing we used was we used the quotient identity here at this equals. And then at this one we used the complementary angle identity. And then this equality, that's just the definition of cotangent theta. Okay. Okay. Example 5, depending on time. Well, we still have 18 minutes, so we're doing okay. So we're going to simplify cosine pi over 2 minus theta times cotangent theta. So in a sense, by simplifying this expression, we're basically making our own identity. Okay? And like I said, the whole point of something like this is you might be in a calculus class, or when you get to calculus, you'll be given some expression like this, and the way it's written, it's not very useful or helpful. So what you have to do is you have to apply some simplifying or do some simplifying using identities first so that it's in a form that's more simplified or more useful. Okay, so anybody have any ideas to what identity I could use?
Definition of cotangent.
Okay, so we could do that. So actually there's a couple things we can do. I guess cotangent we could write as cosine over sine. And is there any identity that I can use on the first term?
Yeah. Cosine of pi over 2 minus theta equals sine of theta.
Okay. So again, this one right here, the cosine pi over 2 minus theta, that can be rewritten as sine theta. And the cotangent of theta can be written as cosine theta over sine theta. Okay. I guess I can be careful about my steps here. So if you multiply two fractions together, you can think of that as sine theta over 1. So this will be sine theta cosine theta over 1 times sine theta. And then what happens to the sine on top and bottom? They'll cancel each other off. And you'll just get cosine theta. Okay, which is it's a lot easier to work with cosine theta than it is to work with that expression. And that's about as simple as we can write it, right? There's not really anywhere to go once you've simplified it down to cosine of theta. Okay. So before we move on, we're gonna do one more example of verifying an identity. There's a couple different ways to think about it. I have the guidelines on the bottom here. You want to make sure you read through these. So when verifying an identity, the very, very most important thing is you cannot begin by assuming the identity is true. Right? I either have to start with the left-hand side and simplify to the right-hand side, or vice versa. So you don't get to assume that what you're starting with is automatically true. Right? You're trying to show that it's true. Okay? So you can't just write down the expression and work with both sides of the equation simultaneously as if you were solving an equation. So number 1, select an expression on one side of the equal sign. Oftentimes the more complicated side, the side that looks more complicated, is the side you want to start with first. Okay? It's a lot easier to take something more complicated and simplify it down than something that's really simple. Then you have to introduce a bunch of stuff that wasn't there. Okay, so generally you work with the more complicated side first. And then number 2 is you start using trig identities in algebra to modify the selected expression until you obtain the expression on the other side. Okay. You might want to always keep in mind to look at the expression you're trying to simplify it into to help you make the right choice. Okay. You'll do things like consider using fundamental identities, converting things to sines and cosines, multiplying by 1 or adding 0. So sometimes you have to be pretty clever when you're doing this. Okay. And then number 3, and this is going to happen. Okay, don't get frustrated. This happened to me a lot when I was learning this. It's not uncommon to attempt a verification more than once. Right? You might start with one side and start working it down. Maybe you start getting farther away from what you're trying to simplify it to. So then you have to start over and try something else. Okay, and that's just the way it goes. It's just when you're first doing this, it takes a lot of practice until you start seeing enough of the forms to getting good ideas at what you should try. Okay. So the key thing there at the end, be persistent. And again, it's not uncommon to try verification more than once. It happens to all of us. Okay. So I'll probably do one of these today, or get through example 5 and 6. That'll leave me with example 7 to do tomorrow, and then I'll make up more equations and more identities that we can practice in class tomorrow. Okay, so example 5 and 6 are going to be verifying the same identity, just doing it 2 different ways. And actually, do I have a number mistake? It should probably be examples 6, 7, and 8. So I think we already did example 5. So technically this is example 6. And what we're going to do is we're going to verify the following trig identity by rewriting the expression on one side in equivalent forms until it's identical to the expression on the other side. So we're going to verify cosine of x over 1 minus sine of x equals secant x plus tangent of x. Okay. And like I said, I'm going to do this in 2 different ways. One way is to start with one side and simplify into the other. The other way is to start with both sides at the same time and simultaneously simplify to a common expression. Okay, so the first one, what I'm going to do is, well, first of all, I have to think about which one's more complicated. Okay, well, this on the right side, it's just a trig function plus a trig function. To me, the left-hand side looks a little bit more complicated because it's a quotient. Okay, so I'm going to start with the left-hand side and simplify into the right-hand side. Okay. Again, we don't just get to assume this is true right at the beginning. Okay, so I have to start with one side or the other. Okay, so I'll start with the left-hand side. Then we use algebra, we use identities. Okay, we have to be clever and maybe introduce some things sometimes. Now, looking at this fraction, can these fractions be split up, or can this fraction be split up as it's written? No, right? Because the sum or difference is in the denominator, not in the numerator. Okay, now look at, I guess it was on the previous page, number 2 at the end. It says sometimes you might have to multiply an expression by something that's equivalent to positive 1. Okay, so that's what we're going to do here. If you ever see a 1 plus or minus sine of x or cosine of x, a good thing to try is multiplying by the reciprocal. Okay, so that's what I'm going to do this time. I'm going to multiply on top and bottom by the reciprocal of the denominator, 1 minus sine of x. So if you ever see 1 plus or minus sine or cosine, a good idea is to use the conjugate. I'm going to leave the numerator unmultiplied out, so cosine of x times 1 plus sine of x. And if you multiply in the denominators, if you multiply something by its reciprocal, you just have to multiply the first terms together to get positive 1. And then minus sine x times plus sine of x will give you a 1 minus sine squared. Reason for this? So if you FOIL, the inner terms and the outer terms would cancel each other, right? Negative sine of x times 1 plus sine of x times 1, that goes away. So you just have to do the 1 times 1 to get 1, minus sine of x times sine of x to get minus sine squared. Okay. Now, anybody think of an identity that involves sine squared and positive 1? Yeah. Would you say, Claire? You said the Pythagorean identity? Okay. So Claire said, maybe since this is 1 and a sine squared, we can maybe use that Pythagorean identity. Okay, well, how do I get a 1 minus sine squared to show up? I can subtract the sine squared to the right, so that cosine squared is really 1 minus sine squared. Okay. So the denominator just becomes cosine squared. And then is there anything now that I can cancel on top and bottom? Right? We got a cosine on top. Wait, hold on, let me pause first. Janae, you got a question? Where are you stuck at? Is it this step or the previous one?
It's the other one.
This one?
Yeah, I'm confused.
Okay, so the numerator stayed the same.
Yeah.
I didn't touch it. Taking the Pythagorean identity, subtracting the sine to the right, I know 1 minus sine squared is cosine squared.
Oh.
So I just replace the denominator with cosine squared.
So then it would be 1 plus sine x over cosine
Mm-hmm.
x.
Yep. Okay, let me just double check. Everybody okay with that last step one more time? Okay. So yeah, and then Claire, you said now what's going to happen is that you can get rid of the cosine on top and get rid of one of the cosines on the bottom. And you said it's 1 plus sine of x over cosine. And now can I split up fractions? Mm-hmm. Yeah, right? If you have a sum or difference in the numerator, then you can split up fractions. So you take every term in the numerator and divide by cosine. So I get 1 over cosine of x, plus sine of x over cosine of x. And then 1 over cosine x equals what? So look what we're trying to simplify to, right? We're trying to get secant plus tangent. And do we basically have it? Yeah, the 1 over cosine is a secant, and the sine over cosine is tangent. And that verifies the identity. So again, I didn't assume that this was true. I started to show it's true. I start with one side of the expression. I use algebra and fundamental identities, plus a couple clever tricks, and we were able to simplify to the right-hand side. Okay. And then this will be the last thing, we'll call it a day. Tomorrow we'll start solving equations using the identities. Okay, so we're going to redo the problem. Now read the directions. Here's the difference this time. We're going to verify the following trig identity by working on each side independently until a common form is obtained. So if I can simplify the left side to something and simplify the right side to the same thing, that's another way to verify the identity. So just real quick, anybody have any more questions? When I was a student in this class, this might have been my favorite thing, just because I thought of it as just some puzzle or game. And I don't know. For me, it was really fun. I don't know if everybody else has the same experience that I have. And then I'll call this is supposed to be example 7. So here's what we're going to do this time. We're going to take the left-hand side, and we're going to take the right-hand side, and we're going to simplify both sides and see if we can simplify to the same thing. All right, if I can simplify the left-hand side to an expression and the right-hand side to some common expression, okay, well then these two would be equal as long as we can simplify them both to the same thing. So, what we can do is, well, we already kind of started simplifying this. I'm not going to go all the way this time. I'm going to kind of do this simultaneously and see. We're basically just meeting in the middle, right? So this one, I think what I did first was multiply top and bottom by 1 plus sine of x. That's how we got the 1 minus sine squared. This one, we can rewrite in terms of sine and cosine. Okay, so we know secant's 1 over cosine, and we know that tangent's sine over cosine. And then when I simplify one more time, I get 1 plus sine of x over cosine of x if I add together using the common denominator. Okay. And then now what I can do up here is this can be